All right. So again, the homework number one will be due on Thursday next week. um, Most of you guys have signed up on Expert here. If you haven't, you can sign up now. And again, you want to work on your problems as early as possible because if you wait, you are not going to get enough time to finish them. Okay, so make sure you get registered and then start working on the problems. Okay. All right. For the disinfecting of the classroom today is Garrett and Anthony. Okay, so after the class, you can spray the surface with the um, solutions on the table here. Okay, so last time we talked about the wave. We gave the definition for a wave, which is the disturbance that propagates from the place it was created. And the focus of us here will be on mechanical waves, which is then further divided into two categories. One is called transverse wave, the other is called longitudinal waves. So in a transverse wave, the median moves, but in the direction that is perpendicular to where the wave is propagating. Okay. On the other hand, a longitudinal wave, the median moves, it actually oscillates back and forth in the direction along with the wave, okay, that propagates. All right, and then for a wave, any type of wave, we can have a few quantities to characterize them: wavelength, period, amplitude, and the speed of the wave can be determined from the wavelength and period, or wavelength and frequency. Okay. Mathematically, we can write out equations to describe the movement of a wave. Okay, so in the physical space, like the XY plane, or sometimes if you have three-dimensional wave, we'll be talking about X, Y, and Z. So for plane wave, let's start with plane wave here. Then the movement of median, any point median, it's going in the y direction, but the wave is propagating in the x direction. Okay, so if that's the wave we are looking at, then you can see wave as to propagate as function. This y is a function of x. All right, and then also y should be also a function of t, because at different time, then the y will be different. Okay, from say from t1 to t2, at 2 times you will expect 2 different y's. So then the y should be a function of both x and t. Okay, x will be a position horizontally, t will be the time variable there. And this is a function of x minus v times t, or x plus v times t. The positive and minus sign here gives you the direction of where wave is moving. So if it's minus sign here, that means the wave is going in the positive x direction. If it's minus a positive here, that means the wave is moving in the minus x direction. Okay. Now wave can comes in as different forms, like sine wave. It can be like square wave, or etc. Most of the time, it could be also like irregular shape. Okay, so but for the simple case, we can look at this wave. It's a sine wave, which can be expressed either as a sine function or cosine function. Okay. So here, this is a function of a times sine kx, where k is defined as 2 pi divided by lambda, and then omega is defined as 2 pi divided by period t. Okay, so this is for a sine wave. Okay, so those two parameters. And again, you can determine the speed of the wave by doing lambda divided by t, or you can use these two quantities, omega, which is the angular frequency, and k is the wave number. Omega divided by k would be also equal to the v. Okay. And then in previous chapter, when we talk about oscillator, if we use a sine or cosine function to represent the oscillation, a lot of times you are not starting from 0 when t is equal to 0. So then there's an extra factor here called phi, or the phase shift quantity, that needed to be added to the sine or cosine function. All right. So then for wave function in general, if this is sine function, if you take sine here, it's sine kx either minus or plus omega t plus this wave shift. Okay. So this is the original wave, initial phase of the wave. Okay. All right. So all this together is called phase of the wave, and then phi is the initial phase. Okay. So that means when x equal to 0 and t equal to 0, right? That's the initial point. So you have a function y as a function of x and t. Now y is the displacement of the median from the equilibrium point. From there, you can actually figure out what's the velocity or the speed of the median. Okay, you'll be doing derivative of y over dt. Okay, so for this notation, I think we have talked about this last semester, but just in case you don't remember or you didn't learn this before. So this for the notation. Let me have my screen over here. Give me 1 second. All right. So this notation V sub Y, all right, of X and T. So this means you are doing derivative, okay, of Y with respect to T. All right. So in physics, if you are doing derivative of Y, this is dy dt. Okay. And then the fact that you have a y subscript here, that means this is the velocity in y direction. Okay, so this is derivative of the y position over dt. So this means that guy. Okay, so right. So you are doing derivative of this dy over dt. Now you are not exactly writing d here. It's because you have two variables here. Okay, so if you are just doing derivative to one of the variables, then you are actually doing partial derivative. Okay, this is called partial derivative. So for this sign, this is called partial derivative. But what it does is the same as if you are doing derivative, just the same as if you are writing dy over dt. Okay, the operation is the same. The notation is slightly different, right? But you are actually doing dy over dt here, just with respect to t, okay, not with respect to x, okay. So then derivative of the y function with respect to t. So, and then you write down the function over here. Let me just pull this on this side here. All right, so doing derivative to this function, okay, so the constant number is still remains. Now the sign, if you are doing derivative of sine, it becomes cosine. All right. And then so then it becomes cosine, okay? And then because you are doing derivative t here, so then in here, you are doing derivative to this variable over here. So then you have a factor of minus omega should come out of the cosine here. So minus omega here. So this is where this minus sign is coming from. It's because you are doing derivative to this sine function, where inside this argument, there's this minus omega in front of t, your variable t, okay? So minus omega comes here, so it becomes minus here, all right? Now, if you remember, this is what we mentioned last semester in chapter 15. So a times omega would be then the velocity, maximum velocity of the median at that point. Okay, so a times omega will give you maximum velocity. So then the velocity of the median is equal to minus a maximum number times cosine function. Okay. Now you have the velocity here. You can figure out the oscillation by doing one more derivative of velocity with respect to t. Okay, so again, doing partial derivative because you are just doing derivative to one of the variables. So you are doing partial derivative here. Okay, partial derivative of velocity in y direction with respect to t, and then that equals to take the function down, this function, actually this function down into the parenthesis here. So then now this 2, a times omega should remain. All right. Cosine should become sine. All right. So that's where this sine is from. Okay. And when you are doing cosine, it becomes not just sine, but minus sine. Okay. So minus. So if you write this, it should be one step missing here. Let me write the whole thing here so you can see. So from so if you're doing partial derivative, let's do this partial t of this minus a omega cosine kx minus omega t plus phi. Okay, this will equal to the constant terms. You can just copy them down. Minus a times omega, right? Now cosine becomes minus sine of the function minus omega t plus phi. Okay, so that, and then because in the argument here you have minus omega t, so then you have minus omega. Okay, goes down there. So you can see you have 3 minus signs, so then become one, just one minus sign. Okay, and then a, that's this omega, that's this omega, so a omega square, and then sine of kx minus omega t plus phi. All right, this is your oscillation in the y direction as a function of x and t. Okay, which is the one on the PowerPoint slide here. Okay. Any questions you guys might have from the derivation here? All right. So if that's clear, we are going to take a look at one example here. So this one says the wave function for a harmonic wave on a stream is y as a function of x and t that is equal to so 1.00 millimeter. This is the amplitude. It's a sine function, 62.8 meters inverse times x. So your k, well, let me just write this notes down so you guys know, understand the question better here. Y as a function of time t that equals to 1.00 millimeter sine of 62.8. This is meters inverse times x plus 314 second inverse times t. All right, so the variables are x and t. Okay, if you compare to the general expression of y equal yxt as a function of xt equals to a sine of kx plus or minus, in this case is plus omega t plus phi, right? So then the question gives you a equals to 1.00 millimeter, right? So that's your known. K equals to 62.8 meters inverse, and then omega equals 314 second inverse. The initial phase phi is 0, right? So though, yes, right. Yeah, the only way is to stop sharing. So then it become larger. Is that better? Let me play on the focus here. So pi is asking in what direction is this wave travel? Okay, asking direction of wave propagation. Pi b is asking you what's the wavelength, and then what's the frequency, and what's the period of the wave. In part C, you're looking for what's the maximum speed. Maximum speed of any point on the stream. in A, it's also asking what's the speed of the wave. Okay, so speed of wave, and then in C is asking what's the maximum speed on the string. So these are two different speeds. Okay, so this is the speed of wave propagation. This is the speed for the median on the string. Okay, it vibrates up and down. So these two are different speeds. Okay. All right. So I think I see a couple of responses in here, but we can take a look at the solution together now. As this is what the problem gives us, so then the first part A here is asking in what direction, because this is part plus, so that means the wave is going in the negative direction. Okay, so then A is in the negative x direction for the wave. Okay, now for the speed of the wave, this is equal to lambda over t, or you can do omega divided by k. Okay, so either way, I think a few slides back we saw this. So this is from definition, but once you introduce these two parameters, then you can also do speed by doing omega divided by k. Okay, the problem gives us k and then omega, so we will be using the second one here. So v is equal to omega divided by k then. Omega is 314. Second inverse k is 62.8. 8 meters inverse. That will give you 5 meters per second. Okay. Or you can keep 3 sig figs because the problem numbers given are in 3 sig figs. So 5.00 meters per second. Okay. So that's your speed for your wave propagation. All right. So just you want to keep note here for wave, okay, when it's propagating, there are two types of speed. One is the speed of wave that is propagating itself. The other one is the median. The median goes up and down or back and forth. Okay, that also has speed. These two does not necessarily have to be the same. Okay, or most often they are not the same. All right. You can imagine like for example, for a magnetic wave, actually it doesn't require median, but something like that. You can have a speed of light. The wave goes like a speed of light, right? For magnetic waves, they are the speed of them are the speed of light. But the medium wouldn't have less speed, right? Because we don't see any physical object moving at less speed, really. Okay. Anyway, so this is part A here. Now part B is asking you to figure out what's the wavelength and period and frequency. Okay. So because k is given, omega is given, and then k is really 2 pi over lambda, right? So then you can solve for your lambda. Lambda then will be 2 pi over k. Okay, so this will be 2 pi over the k is given as 62.8 meters inverse. That would be 0.10 meters. Okay, for the wavelength. Now omega is equal to 2 pi over frequency, I think, period. All right, so then period is equal to 2 pi over omega. So 2 pi over 314 second inverse. That would be 0.02 seconds. Okay. Now the fact I'm keeping extra zeros to the right because I want to keep 3 sig figs. Okay, just to be consistent with the problem. Once you have t, then you can solve for your frequency. Frequency is 1 over t. Okay, so 1 over 0.0200 second, that will give you 50 hertz. Okay, for the frequency. Passy Vy max. Okay, so this one, I think it's the slides ahead before that. So if you go one more slide up, it will be, so this is the maximum, right? Vy maximum, that will be equal to A times omega. Okay, so you'll be doing just A times omega for your Vy max, which is the maximum speed of the any point on the string, which means the median. Okay, so A times omega, A is 1.00 millimeter times omega. Omega is given as 314 meters per seconds inverse. Okay, so then this would be you need to convert millimeter into meters. Okay, if you want to keep SI units, so times 10 to the minus 3 meters here. Then this would be 0.314 meters per second. Okay, if that's in meters per second. All right. Questions you guys might have? Is less silence just a test or a real one? All right. Okay, so that's the wave function. So for this one, this is for general case. I think you will see this equation at the bottom here often if you are going to take electromagnetic waves. Okay, so this is the one of the fundamental equations for electromagnetic wave. But basically, so the derivatives we did earlier were with respect to time t variable. Okay, now if you do the wave function, do derivative to the wave function with respect to the position x variable. All right, so if you are doing this one time, then it gives you the slope of your wave function. Okay, so doing it one time, it will give you sine becomes cosine, then the k in front of x comes out. Okay, so a times k cosine. All right. Now doing it twice will give you curvature of your function. So then you are doing again derivative with respect to x to this guy. All right. So then ak square, you should get an ak square. Now cosine will become negative sign. So then negative ak square sine. Okay. So this is the final result. All right. And now when we are doing double derivatives of the wave function with respect to t, this is what we get. Okay, so if you compare this guy and this guy, you'll see the same minus a, all right, and then sine functions. Okay, but there's difference here. This is omega square, this is k square. All right, now this two, if you remember, this is one of the equations we mentioned earlier. Velocity is equal to omega divided by k. So then combine this one, this guy, and this guy, these three pieces of information together, you'll realize that double derivative to the x, all right, is equal to 1 over v squared times double derivative of the function with respect to t. Okay, so this is one of the fundamental wave equation, or this is called wave equation. Okay, one of the fundamental equation for electromagnetic waves. All right. Okay, so any questions about this one? If not, then we'll check on the next section of this chapter, the wave speed on a stretch stream. Okay, so what determines the speed of the wave in a stream? Okay, so you can think about, so there's physical quantities for a stream. You can pull the string very tightly. You can pull it not so tightly. Okay, so that's one of the factors. So how much tension you apply into the string. Okay, so that's one. And then secondly, um, what's the how heavy is the string itself? Okay, you can have a very thin or very thick string. You can have a heavy one or a small one. So those are the two factors that determines the speed of the wave in the string. Okay, and if tension increases, then the speed of the wave will increase. Okay, so that's from the experimental observation. All right. Now, the another factor like how thin or how thick is the string, that can be described by the linear mass density of the string. Okay, so for linear density, you do the mass divided by the length of it. Okay, so that's the linear density of it. M divided by L. We use symbol mu for that. So mu in this case is the mass per length. Okay. Now previous semester we used mu as coefficient of friction, but this time we use as the mass per unit length. Okay. All right. So let's take a look on those quantities. All right, because we say the speed on the stream, so this has a dimension of meters per second or units of meters per second, the dimension for speed. Okay, now tension force that has a unit of newtons, which is equivalent to kilograms times meters per second square. according to Newton's second law, force equals to mass times acceleration. All right. Now, mass per unit length will be the mass divided by length, so kilogram divided by meters. Okay. So this quantity is determined by these two quantities, right? So one of the lab you guys did in the first semester was the determine the period of a pendulum bob. Okay, in that lab, it describes you the method how to do dimension analysis and come up with the hypothesis, like the equation for that quantity t. In here, we'll be doing the same. Okay, so we are going to say the speed is determined by these two quantities, the tension force and then the mass per unit length, but it might be in power of say 1 or 2 or maybe half or maybe 3. So we say we don't know about that. So let's say just a or f times to the a power and then times mu to the b power. Okay, we are going to determine a and b. All right. Now for dimension analysis, for this speed, it has the unit of meters per second, right? So you write down on the left hand side, this is meters per second. Now for force, it's going to be kilogram times meters times second square or divide by second square, okay? And then rise it to the power of A. For this guy, it's kilogram over meters, okay? To the power of B. You see there's kilogram here in the first parentheses, and then in the second set of parentheses, there's kilogram too, okay? So you can take them out. So then kilogram should be raised to the power of A plus B. For meters here is power to the A, and then meters here to power of minus B because meters is in the denominator. So then meters to the power of A minus B. And then second, okay, there's still second there remaining. It should have the power of minus 2A, okay? So this is the right hand side, this is the left hand side. On the left hand side, you see there's no kilogram, all right? So that means A plus B will be 0, right? Let's get rid of the kilogram for the unit, okay? And then, so let me just write down here, somewhere here, I'll zoom it in a couple of minutes, or a couple of seconds there. So A plus B should be equal to 0 because on the left hand side, there's no kilogram, all right? On the left hand side, the meters has a power of 1, right? Just meters, that means meters to the 1 power. So then on the left hand side, the power for meter is 1. Now power for the meter is A minus B on the right hand side. Okay, so then that means A minus B equals to 1. Okay. On the left hand side, the second is in the denominator. That means power for the second is minus 1. So then minus 1 equals to minus 2A, right? All right. And then we have think V equals to F to the power A times mu to the power B. That's our hypothesis, okay, our theory. All right, so you can solve for A and B, right, from here. From this guy, it tells you A is equal to 1/2. All right, you can take this back into either this one or that one. So then that's going to tell you B is equal to minus 1/2, okay? So they're consistent. If you solve B from here, you can take B back into here. You'll see that, right? If this is 1/2, this should be minus 1/2. And then 1/2 minus 1/2 gives you 1. Okay, so that's consistent there. So your A should be 1/2, B should be minus 1/2. So then velocity speed should be equal to F to the power of 1/2, right? Times mu to the power of 1 minus 1/2. Okay. Now power of 1/2 is the square root, right? So then this is square root of F divided by mu, right? If you have minus, that means in the denominator. So F divided by mu, that's the speed, okay? So from the dimension analysis, you can figure out that the speed of the wave on the stream, that should be equal to square root of the force, the tension force divided by is linear mass density of mu. Okay. All right. So then let's go back to the PowerPoint slide here. All right. So this is the conclusion. Speed of wave on a stream v is equal to f divided by u by mu, and then take square root. Okay, where f is the tension in the stream, mu is the linear density of the string, or mass of the string divided by the length. All right. We'll take a look the example on guitar strings. All right. So guitar strings, they are made of steel. Okay. So if you have two of those strings that have the same length, A has a diameter of 0.50 millimeter and is under 410.0 newtons of tension. String B has a diameter of 1.0 millimeter and is under the tension of 820.0 Newton. Find the ratio of wave speeds in the two streams. So VA over VB. Now you probably would start with this equation of V equals to F divided by U, okay, where where mu is equal to the mass divided by the length. Now there are some informations given here. Okay, I'm going to write down here. So RA, or I think it says diameter. So DA equals to 0.50 millimeter. DB equals to 1.0 millimeter. Tension in A is equal to 410. Tension in B is equal to 820. And that's about it. You're looking for VA over VB. What's the ratio of this? So our tension, we can use F. Okay, so F, because in our formula we say F, so let's just use F. FA and FB. And then it says length A and B are the same. LA equal to LB. Now let's assumption here that's not specified, but you can assume that the density of the two materials is the same. Okay, so rho A and rho B are the same because they are both made of steel. Okay, so the same materials, that means the density is the same. But however, density doesn't mean linear density is the same, right? This is volume density, but this is probably not the same. So UA and UB are not necessarily the same. All right. So you guys can give it a try. And then we can take the solution together in a few seconds, okay? Or a few minutes. If you have your response, you can submit the response. Now the fact that linear density is not the same because they are not the same thickness, okay? So one is thicker than the other one, so that means that one is probably having larger linear density than the other one. Okay. All right. I think I saw a few responses in here. Unfortunately, only one is correct. Okay, we'll see who gets this one correct. All right. So I don't think we are given enough information to figure out each speed individually. Okay, so then the best way to do here is just try to express the speed of the the wave in terms of the given quantities or some quantities, and then you might figure out later on that some of them can be canceled out. Okay, so let's see here. So V is equal to tension force divided by mu, right? And then square root. Now, tension for each case is given. So then you can leave it as F, but U is not. So U should be equal to the mass divided by length, right? Length is not given, mass is not given. But the mass can be expressed as the rho times the volume, right? Divided by L. Now volume for the guitar strings, it should be like a cylinder, right? So it's a cylinder, a very thin cylinder you can imagine. So the length is L, and then diameters are given. So D are given, okay? So then you can express mu as, so rho times volume. Volume will be equal to the cross-sectional area times the length of the cylinder, right? Cross-sectional area should be, if we are given diameter, then it's pi over 4 d squared, right? Divided by L. Okay, so that's mu. You can write this as pi times rho times d squared divided by 4 times L. Okay, in that case, denominator goes to the denominator. All right, so then you are looking for VA over VB. So your V in this case then is equal to F divided by all this, right? Pi times rho times d squared divided by 4L, right? And then square root. Now, this can go up there because it's denominator in the denominator. So 4 times F times L divided by pi rho d squared, square root, okay? So for A, then this is equal to 4 times FA times LA divided by pi rho d squared and then square root, okay? So this is just for VA and then divided by, so the top here is VA. At the bottom here, you should have square root of 4 FB LB divided by pi rho D. This is DA on that one. DB should be on this one, okay? DB squared. So the bottom here is VB, all right? Maybe something like that, more clear. Now you can see 4 and 4 will cancel out, right? Pi and rho will cancel out pi and rho, right? Now LA and LB, LA and LB are the same length, right? It tells you they are the same length. LA equal to LB. So then this would cancel out this guy. Okay. You can see a lot of cancellation there. Now it becomes VA over VB equals 2. On the top here, FA divided by DA square root divided by square root of FB dB square. Okay. Now the remaining quantities here have, they all have numbers. Okay. So you can put in the numbers here at this point, and then see what's your final result. Okay. So FA is 410.0 newtons divided by 0.5 millimeters square. This is square root there. And in the bottom here, 280 divided by 1.0 millimeter square and then square root. Okay. All right. So now right here, if you look closely, so this is 410, this is 820. So then this will cancel out that one, but with 2 here, right? Because this is twice of that. So 1 there, 2 here, right? And then this guy and this guy, you can leave it there, but the units can cancel out, right? So you don't have to worry about the units, okay? So at the end over here, you can decide to do like this one, write this as 1, this as 2 as well, okay, if you want. But at this point, I think you can put in your calculators for everything. But this is square root of 2, okay, for the final answer here. All right. Because it will be 4 on the top here. If you do 1 divided by 0.5, remember there's a square here. So then becomes 4 on the top here. And then this is 2 in the bottom. So 4 divided by 2, but remember there's a square root. Okay, so the final answer should be square root of 2. All right. Any questions you guys might have on this one here? All right. So if you are clear, I think we'll stop here for today.